So in the next couple of examples, we're actually just going to be looking at trying to find some equations of some of these tangent lines to a variety of different curves. First off, we're going to be looking at the curve y equals x to the fourth plus 5e to the x, and we're going to be interested in finding this tangent line at this point 0, 5. To do this, we're actually going to use this really nice connection between this knowledge about derivatives and slopes of these tangent lines. That is, I know my derivative evaluated at this x point, in this case if I call it just a c, is going to equal the slope of the tangent line at that point x equals c. And that's exactly what makes all of this stuff work. In this case, I want to find the tangent line at the point 0, 5, giving me an x value of 0. And to do this, then, I need to find what is my derivative at 0. That is, first up, I need to compute what is y prime of 0. To do that, I actually have to find the derivative of this thing, and then once I know the derivative, I'm going to evaluate this thing at 0. To compute this derivative, I'm going to see y prime is going to be equal to the derivative of x to the fourth plus 5e to the x. I'm going to use this kind of sum rule to distribute this d dx, and then I'm actually going to use this constant multiple to actually kick out the 5. What this gives me is a derivative of x to the fourth, and then plus this 5, and then I'm going to differentiate this exponential. We know this x to the fourth can just be attacked using this power rule, giving me a 4x cubed. The 5 is just a 5, and I know this exponential has this really awesome property that the derivative actually does not change the function, so it's just going to be a 5e to the x. And that's exactly what my derivative is going to be in this case. What I need to find then is what this thing is actually going to kick out at 0. Finding this, I'm going to have a y prime evaluated at 0. All I'm going to do is just plug in 0 anywhere I see an x in this function, giving me a 4 times 0 cubed plus a 5 times e to the 0. This part's going to kick out a 0. This is going to be a 5. E to the 0 is actually just a 1, ultimately giving me a slope of 5. Then this line is going to be this y minus y1 equals my slope times x minus x1. What I'm going to have is a y minus my y value, which is a 5, equals my slope, which I just found, is a 5. And then x minus my x value, which is a 0. Cleaning all this up, you actually see that this is pretty nice. It's just going to become a 5x plus 5. And that's exactly what my tangent line is going to take at this very special point 0, 5. The way that we found that is we differentiated this function, evaluated this thing actually at the x point in question, and then just dumped all of this stuff into our kind of classic point slope formula for our line. Next up, we're going to be doing the exact same thing, but changing our function just slightly. In this case, I'm going to have one of these quartic functions. It's got some kind of gross fractions going around, but structurally, we're going to be doing the exact same thing. My x point in question is going to be a -2 this time, so I actually need to find the derivative of this thing at -2. That is, I want to find dy dx when x is equal to -2. To do that, I actually have to go ahead and differentiate this thing, finding out that dy dx is going to be the derivative of that giant expression, which is a 1 minus an x squared over 2 plus an x to the fourth over a 24. Applying this kind of sum and difference rule to this thing, I'm going to see a derivative, in this case, of my constant 1. In this case, this x squared is being divided by a 2. There's also a negative sign in front of that thing. I'm going to represent that as a little -1/2 that comes out, giving me a derivative just of that x squared part. Likewise, I'm going to view this kind of 1/24 coming out with this constant multiple rule, having a 1 over 24, and then a derivative, in this case, of an x to the fourth. Alright, so now I just got to clean this up just a little bit. The derivatives of constants we know are 0, giving me a 0 here. I'm going to have this -1/2. The derivative of x squared is a 2x. And I'm going to have a 1/24 multiplied by the derivative of x to the fourth, which is a 4x cubed. Trying to clean this up just a little bit, I have a -1/2 and a 2, which is going to be a -1, giving me a -x. And then I'm going to have a 4 divided by a 24, which I guess is something like a 1/6, and there's still this x cubed. So what I need to do is I need to compute this thing evaluated at -2. And there's a couple different notations we can do for this. I'm kind of intentionally going through just a couple different ways you may see this. But my slope in this case is going to be my derivative dy dx, and I'm evaluating this thing when x is equal to -2. It's kind of the fanciest, weirdest way to represent this derivative, but it all works out. Okay, plugging in -2 into my derivative is going to give me a negative with a -2, and then a plus 1/6 with a -2 cubed. The double negative is going to give me a +2, and then I'm going to have a -2 cubed, which is actually a -8, over a 6 in this case. And trying to clean this up, I'm going to have a 2 minus an 8/6. 8/6 is actually just I guess a 4/3. A 2 is actually viewed as a 6/3, so I'm going to take a 6/3 minus a 4/3, giving me a +2/3. And that's exactly what my slope is going to be in this case. I have a slope of my tangent line, which is a 2/3, and now I actually want to go ahead and create this line. I'm going to have my y minus my y value, which is a y minus a -1/3, equals my slope, which is a 2/3, and then I'm going to have x minus my x value, which is a -2. There's a whole bunch of kind of really gross fractions going on, but it's kind of structurally the exact same as that last problem. What is this? A y plus a 1/3 equals a 2/3 x. That's actually going to be a +2 multiplied by that 2/3 is going to give me a +4/3, which is kind of nice to see floating around as well. And then what I'm going to do is I'm going to subtract off the 1/3, giving me y equals 2/3 x, a 4/3, and then removing off this 1/3 is going to give me a 3/3, which is just a 1. In this case, I end up with this slope of this line being 2/3. I actually have a nice little y-intercept occurring at 1, giving me that my overall tangent line is of the form y equals 2/3 x plus 1. You can see that these two problems are actually very similar. Kind of the question was, I need to evaluate my derivative at this specific point. In this case, I actually use this kind of y prime notation, and over here I've actually used this kind of dy dx notation. But the process is the exact same. I'm just kind of introducing a couple different ways of seeing these things. Kind of depending on where you're going in your careers, you might see certain notations a bit more frequently than others.